When we are dealing with parabolic functions, it's important to know the shape of that function. So if we have a positive A shape, it will look like a smiley face. So basically it would look like this. Now our turning point would be situated about here. Now let's discuss when is this function increasing and when is this function decreasing. So if you remember from our last class, we mentioned that whenever there's a positive linear gradient, that is increasing, and whenever it looks like a negative linear gradient, that is decreasing. So if you notice the right hand side of our parabolic function that has a smiley face looks like a positive linear gradient. If you look at it, it kind of looks like this. So we can see that the right side is increasing, whereas the left side is decreasing. Something important to take note of: when a function is increasing, what that means is that as the value of x increases, the value of d, or rather the value of y, also increases. So as your x value increases, your y value also increases. So we are going to denote this point here as our x value of our turning point. So if we were to answer this question, when is it increasing? That would be for the values of x greater than the x value of our turning point. Now, how do we know which way our inequality sign is supposed to face? A method that you can use is, because we're saying that for all the values on the right of our turning point, so we draw an arrow that faces towards the right, and if you look at that arrow, the arrowhead is pointing right. That is why our inequality sign points right as well. So you can just basically copy the direction of your arrow. Now if it's a decreasing function, if you look at the left hand side of this parabolic function, the left hand side looks like a decreasing or a negative gradient linear function. So we know that for all the values to the left of the turning point, this function is going to be decreasing. So if we were to draw our arrow, draw arrowhead, and that shows that to the left side, so our arrowhead is pointing left, so we can just copy that, and that means that for all the values of x less than the x value of our turning point, this function is a decreasing function. So let's move on to our negative a shape. So that is when the value of a is negative. We then have a sad face function. So it's going to look like this. Now if we assume this point to be our turning point, now same as before, when is our function increasing and when is our function decreasing? So let's start with the right hand side of our negative shape parabolic function. So if you look at the right hand side, it kind of looks like the negative gradient of your linear function. And we said that whenever we have a negative gradient, we then know that it's a decreasing function. Because as you can see, the value of x is getting bigger as you go to the right, but the value of y is getting smaller. So that is a decreasing function. So if we put our arrow, we're going to the right. So we just copy the arrowhead direction. So x greater than the x value of our turning point. Now, if we look at the left side of our function, we can see that the left side kind of looks like a positive linear gradient. And as you can see, as the x value increases, the y value is also increasing. So that is then going to be a increasing function. So draw our arrowhead. As you can see, the arrowhead is pointing to the left. Therefore, that's the direction that we are going to use in our inequality. So for what values of x is this parabolic function increasing? It's increasing for all the values of x that are less than the x value of our turning point. So if our turning point was 2, it would be x less than 2. Now that's our shape. Let's move on to point number 2, discussing the 3 different forms of a parabolic function. So when we're dealing with a parabolic function, we have 3 different forms. The first being our standard form that you're more used to seeing, which is represented by y equals ax squared plus bx plus c. That is point number 2.1. Now, our standard form is what you usually see and what we usually write our final answer in. Now, there's 2 other forms that can be present, which is our turning point form, which is represented by y equals x minus p all squared plus q, where p and q represent the x and y values of your turning point. Now, p also represents the horizontal shift, and q represents the vertical shift. So p has to go from our standard form to our turning point form, we can complete squares. So this is something that you learned in algebra, I think in grade 10. So if we complete squares on a standard form, it'll then turn into a turning point form. Now our third and final form is our x-intercept form. Now that is represented by the equation y equals a into x minus x1 times x minus x2, where x1 and x2 represent the x values of our x-intercepts. Now, in order for us to go from our standard form into our x-intercept form, all we need to do is factorize the trinomial. Now, if we want to go from our turning point form or our x-intercept form to our standard form, all we need to do is just expand our function and then just simplify. So let us move on to an example dealing with finding the equations of a parabolic function. Now, in order for us to find the equation of a parabolic function, we either need to use our turning point form or our x-intercept form. So that was the importance of learning or understanding those forms. If we are given a turning point coordinate and a random coordinate, we will use our turning point form. If we are given the x-intercept and a random coordinate, we will use our x-intercept form. So let's quickly draw a function. So this function cuts through the origin, and let's give it a turning point of 2 and negative 4. So because we are given the turning point and a random coordinate, which is our origin, we can now use our turning point form. So our turning point form is y equals a into x minus p squared plus q. So because we have our turning point, we are now going to substitute our turning point into this formula. So our x value of our turning point is 2, and our y value of our turning point is negative 4. So like we mentioned previously, P and Q represent the X and Y values of our turning point. Now from here, we can substitute our random coordinate. So we know that our random coordinate is represented by 0 and 0. So that is our X and Y values. So this is going to be 0 into A times 0 minus 2 all squared minus 4. From here, we can take this negative 4 to the left, and it will become positive 4 equals 4a. Because we know that 0 minus 2 is negative 2, all squared becomes positive 4. From here, we have a equals 1. Now, in both methods, whether you're dealing with your turning point form or your x-intercept form, the goal is to solve for a. So once you solve for a, you are then able to substitute a, p, and q into whichever form, or more specifically into your turning point form, which will then allow you to get your function. So even when you're dealing with your x-intercept form, the goal is to solve for a so that you can substitute a, x1, x2 into your x-intercept form in order for you to find your function. So now that we have a, let's rewrite our turning point form. We're now going to substitute our value of a, which is 1, our value of p, which is 2, and our value of q, which is negative 4. From here, we are then going to simplify. So we have x minus 2 times x minus 2 minus 4. That then gives us x squared minus 4x plus 4 minus 4. And therefore, our standard form of f is then equal to x squared minus 4x. So that is the equation of our function of f. So all we needed to do was step number 1. We needed to substitute our turning points. Once we've substituted our turning points, our step number 2 was to substitute our random coordinate. After we substituted our random coordinate, we needed to find our value of a. Once we found a, our last and final step was to substitute a, p, and q and simplify. So there's only 4 steps involved. The most important thing is to identify what you were given. So because we were given a turning point and a random coordinate, we use the x-intercept form. If we were given the x-intercepts and a random coordinate, we would then be able to use our x-intercept form. So in our next example, we are going to use our x-intercepts and our x-intercept form to find our equation of f. So if we have our parabolic graph, and let's make this our first x-intercept, let's give it a value of 2. Let's make this our second x-intercept, and we'll give it a value of x equals 5. Now we need a random coordinate, so let's make this our random coordinate. Let's give it a value of 1 and 4. So we have our x-intercepts, which is 2 and 5. We have a random coordinate, which is 1 and 4. So now we are going to use our x-intercept form because we are given our x-intercepts and our random coordinate. If we were given our turning point and a random coordinate, we would use our turning point form. So our x-intercept form is y equals a into x minus x1, x minus x2, where x1 and x2 are our x-intercepts. So our first step is to sub x1 equals 2 and x2 equals 5. So we sub those two x-intercepts in. Now next we are going to substitute our random coordinate, which is y equals 4 and x equals 1. So our y value is 4 and our x value is 1. Now from this point we can put both those brackets onto our calculator. So open a bracket, 1 minus 2, close the bracket, open a new bracket, 1 minus 5, and that gives us 4. So we have 4 equals 4a. From here we can divide both sides by 4, and our a value is therefore 1. Now that we've found our a value, we can now substitute our value of x1, our value of x2, and our value of a into our x-intercept form. So our value of a is 1 minus our value of x1 is 2, and our value of x2 is 5. From here, all we need to do is expand. So we know 1 times anything is going to remain the same. Now, we're going to use our FOIL method to expand inside of the bracket. So we've got x times x, that gives us x squared. We've got x times negative 5, that gives us negative 5x. We have negative 2 times x, that gives us negative 2x, and negative 2 times negative 5 gives us positive 10. Now, from here we see that we have two like terms. So we can add up our like terms. That's going to give us negative 7x plus 10. So our equation of f using our x-intercept form now becomes y equals x squared minus 7x plus 10. We can also write this as f of x equals x squared minus 7x plus 10. We don't have to leave it in y. We can also conclude and write it in the f of x form. Now let's move on to point number 3 that discusses our turning points. How do we find our turning point? So we know that our turning point is the point at which the graph changes direction. So we can find our turning point in one of 3 ways. The first being we can use our turning point formula. So how we find the x value of our turning point is by using the formula x equals negative b over 2a, whereby a and b come from our standard point form, and this is our a, this is our b. So a would be the coefficient of x squared, or the number in front of x squared, whereas b would be the coefficient of x, or the number in front of x. Now we can plug all of these values into our formula, can simplify our formula, put it on our calculator, and we can get a final value of our x coordinate of our turning point. If we want to get our y value of our turning point, all we do is we substitute the x value into our original formula or into our original function, and that will give us the y value. That will then be our turning point coordinates. The second method that we can use is to use the midpoint formula and involve our x-intercepts. So alternatively, what we can do is we can have our x of TP equals x1 plus x2 all over 2. So x1 and x2 represent our x-intercepts. So if we were to substitute our x-intercepts into this formula, we would then end up with the x value of our turning point, because the x value of our turning point is the midpoint of our x-intercepts. Then if we want to get our y value of our turning point, it's the same process. We substitute the x value into the original function, and that will give us our y value. Now, the last and final method that you can use is to use your turning point formula. Or not your turning point formula, let's rephrase that. You can use your turning point form. So we know that our turning point form is given by y equals a into x minus p squared plus q. And our turning point coordinates are given by p and q. So if we want to get our turning point coordinates from our turning point form, all we have to do is extract the p value and extract the q value out of the form or out of the equation. So those are the three methods that we can use in order to find our turning point coordinates. We'll do a few examples on turning point in a minute. Let's just go through our range and our domain before we move on to that. So let's start with range. So if we are dealing with range, range involves all of the y values that our graph touches. So there's two methods of finding range depending on what shape of function you have. So if you have a smiley face shape, or if you have a sad face shape, your range will kind of differ slightly. So if you have a smiley face shape, let's do that first. So if you have this smiley face shape, because your function starts at a minimum point, the lowest point, your range is going to start from this point and go upwards because your graph extends upwards. So that is going to be your range. It's going to start at your minimum and then go upwards. So that is why we'll say our range is y greater than or equal to our q value, whereby our q value represents the y coordinate or the y value of our turning point. Now, what is important to take note of is that in most cases, you'll first have to find your y value, your turning point, before you can find your range. Or sometimes in a previous question, you would have already found your turning point, so you can just extract the q value. Now, we use the inequality greater than or equal to because we are including the coordinate or the value of q, because our graph does in fact touch the q value. If it didn't touch the q value, we would only have y greater than q, not y greater than or equal to q. So that's an important note. Now let's use the sad face one. So if our function is in a negative shape, in a sad face shape, we have a maximum point, the highest point, represented by q, because q represents the lowest or the highest point in our graph depending on the shape. So if we have a sad face graph, our range is going to start from our highest point or our maximum point and go downwards because our graph is extending downwards. So that's why we have our range as y less than or equal to q, or an alternative notation is to just have it as y an element from negative infinity until q. Now, a slight correction, this is supposed to be a squared bracket because we are touching the value of q. If the graph does not include the value of q, then it would be a rounded bracket, and infinity or negative infinity is always a rounded bracket. The rounded bracket just indicates we are not including that value, whereas a squared bracket indicates that that value is included. Now, if we are dealing with range and domain, or rather just domain, which is 0.5, we know that the domain is all the x values that the graph touches. So when we're dealing with a normal unrestricted parabolic function, the domain is just from negative infinity to positive infinity, or you can also say x an element of real numbers. Because if the domain is unrestricted, the graph or our parabolic function is going to touch all of the x values. The only time that the domain is not x an element of real numbers is when the domain is restricted. Now we'll go further into detail regarding restricted domains when we do inverse functions. So let's continue to our last point, point number 6, before we go and do some examples. So if we want to find the axis of symmetry, an axis of symmetry is just basically cutting the graph at a point whereby the one side is a mirror image of the other side. So if we look at our turning point, because that is the middle of our graph, the turning point. If we were to cut our function on the x value of our turning point, our function would be symmetrical. The left-hand side would be the same as our right-hand side. That is why our point of symmetry, or our value of our symmetry, is x equals the x value of our turning point. For example, if our x value of our turning point was positive 2, our answer to our axis of symmetry question would be the graph is symmetrical about x equals 2. Now, with that out of the way, let us move on to our examples. So our first example is given the function f of x equals x squared plus 4x plus 3, determine the following. So we need to find the coordinates of the turning point of f. So because we are not given the x-intercepts, we can't use the midpoint formula. Because we are not given the turning point form, we can't use the turning point form to extract the p and q values. So our only option in this case is to write down our turning point formula, substitute our value of b and a, and get our turning point coordinates. We can convert our standard form into turning point form, but that would take longer. The shortest and easiest way would just be to use our turning point formula. So we know our turning point formula is x of tp equals negative b over 2a. From here, we know that our value of b is the coefficient of x, which is 4. So carry the negative, substitute 4 over, carry the 2 and substitute our value of a. So our value of a is the coefficient of x squared, and that is 1. So once we put this on our calculator, we end up with negative 2. So let's just write that down here so we can use the right hand side for finding y. Now let's find y. So if we want to find y, all we need to do is substitute x into the original function, and that will give us y. So sub negative 2 squared plus 4 into negative 2 plus 3. Once we put that onto our calculator, negative 2 all squared plus 4 times negative 2 plus 3, that is then going to give us negative 1. So we can then conclude that our turning point coordinates are therefore negative 2 and negative 1. Now, if we want to find the domain and range of our function f, keep in mind that because our function f is not restricted, our domain is then going to be x an element of real numbers. Now, if we need to find range, our first step is to identify whether this is a greater than 0 or a less than 0. Now, because we have a greater than 0, it's a positive graph, we then know it's going to be a smiley face. So, you can represent it like that. This is going to be our turning point, which has coordinates negative 2 and negative 1. So, our range is going to be from the minimum point, which is Q, going up. It's going to touch all the values greater than Q. So our range is therefore going to be y greater than or equal to our value of Q, which is negative 1. An alternative notation would be to represent it as y an element from negative 1 until positive infinity. And negative 1 is in a square bracket because we are including that value. Let's move on to our next example, which is the value, or rather the x value of the axis of symmetry. So we need to find the x value of our axis of symmetry. So let's draw our function. This is going to be our turning point, which has coordinates negative 2 and negative 1. If we were to cut our function on this turning point, the left hand side would be a mirror image of the right hand side. So therefore we can conclude that our axis of symmetry is x equals the x value of our turning point, which is negative 2. Now let's do another example of the exact same questions but with a negative graph. So here we have to find the coordinates of our turning point. So we have our formula x of tp equals negative b over 2a. Now we carry over our negative sign, open a bracket so we can substitute. And we can see that our value of b, which is the coefficient of x, is negative 4. So be careful, don't forget about the negative sign in front of b just because you have a negative value. Always carry over your negative sign and then substitute so you don't forget it. If you forget your negative sign, your answer is going to end up being opposite to the sign that you're supposed to have. For example, if your final answer is supposed to be negative, you could end up with a positive value, which is wrong. So bring down our 2, substitute our value of a, and as we can see, our value of a, which is the coefficient of x squared, is negative 1. From here, we can see that our x value of our turning point is then equal to negative times negative 4 gives us positive 4, and 2 times negative 1 gives us negative 2. Therefore, we end up with negative 2. Now, if we want to find our y value of our turning point, so we can have y equals, or we can even write it as f of -2 equals, whichever, it doesn't matter, sub it in. So bring down your negative sign, open a bracket, substitute -2 squared minus 4, open a bracket to substitute -2 minus 3. From here, we can put all of this on our calculator. So we have negative into -2 all squared minus 4 into -2 minus 3. And that is going to give us a value of positive 1. Therefore, we can conclude that our turning point coordinates are -2 and positive 1. If we want to find our range and domain, domain is still the same, x an element of real numbers, because our function is unrestricted. But if we want to find our range, let's start by drawing our negative shape parabolic function. So we know that this turning point over here, which is represented by the coordinates -2 and positive 1, is the highest point, or you can call it the max or maximum value of our graph. Now our range represents from this point all the way going down, because these are the values that our graph touches, or the y values that our graph touches. So our range is therefore y less than or equal to the value of q, which is 1. Now that is our value of q. An alternative notation would be to represent it as y an element from -infinity to positive 1. Now, if we're using the second notation, your smallest value has to be on the left and your biggest value on the right, because -infinity is your smallest, or you can say your minimum, and 1 would be your maximum or your biggest value in this case. So always remember, when you're using this notation, it's always smallest to biggest. Now, let us find our axis of symmetry. So if we draw our graph once more, and this would represent our turning point, which has coordinates -2 and positive 1. If we were to cut our graph along this x value, we know that the left hand side is going to be equal to the right hand side. Therefore, our x value of symmetry is x equals -2. Now, let us go back to our notes. So let's do point number 7 that deals with reflections. Once we're done with that, we will move on to the last point in our notes, which is inverse functions. That is when we'll deal with restricting our domain. Point number 7, reflections. 7.1. Reflect the graph about the x-axis. So if we were to reflect our graph about our x-axis, that will result in a change in our y values. So let's just quickly draw our axis. So if we have our graph f, let's give it a positive shape. Now, if we were to reflect our graph f about the x-axis, that means our reflection would be on this line here. So we would basically fold our paper about this line, and the top of our paper needs to touch the bottom of our paper. So that is folding our paper along the x-axis. Now once we fold our paper, or once we reflect our graph about the x-axis, our new graph that will form will have the same x-intercepts, but the shape of it would be different. It would then become a negative shape. So it would look something like this. And the value of our turning point, the x value would remain the same, but the y value would change. So if originally the y value of our turning point was -1. The new y value of our turning point in our reflected graph would be +1. So all we are doing is making, or rather let's not say making, all we are doing is basically changing our y values. So we're multiplying it by a negative essentially. So if it's +1, it will become -1. If it's -2, it will become +2. The x values stay the same, but the y values change. So if we want to reflect about the x-axis and change the y values, this is essentially what we are doing, multiplying our y values by a negative. So let us do that. So the reflection would then become negative f of x equals negative into x squared minus x minus 6. So we multiply everything by negative. That is then going to give us y equals negative x squared plus x plus 6. So we've multiplied our entire function by negative. Because keep in mind, this whole thing here, this whole function, that represents the y value, that entire function. Because we have f of x equals, which is the same as saying y equals. So y is equal to this whole function. That is why we multiply the whole function by a negative, because that is changing the y value. Now, let's move on to point 7.2 to reflect the graph about the y-axis. So if we want to reflect about the y-axis, that is going to change the value of x. So let's do a quick example. So this is our axis. Let's have our function. Let's keep it as a positive function. Now, if we were to reflect this positive function about the y-axis, that means we need to fold our paper along the y-axis. So the right of our paper is going to touch the left of our paper. That is then going to change our x value. So let's slightly change our graph and move this graph more to the left. So if our graph was like this, whereby our turning point was more to the left, let's give this a turning point of -1. If we were to reflect our graph about our y-axis and fold our paper along this line, our new graph would then be something like this, whereby our new x value of our turning point would be +1. So as you can see, the x value has changed, but the y value will remain the same. So if we want to change our x value, all we need to do is multiply our x by a negative. So let's do that here. So we need to reflect x squared minus x minus 6 about the y-axis. So all we are going to do is, where we have x, substitute it with, in brackets, negative x. So here we have x, so we're going to substitute it with negative x and then squared, minus, now here we have x, so we substitute it with brackets negative x, and this -6 doesn't have any x, so we write it as is. Therefore, our equation is then going to be negative x all squared becomes positive x squared, because negative times negative becomes positive. This negative times negative x will become positive x, and that stays -6. So that is how we would reflect our graph about the y-axis. Now, let's move on to inverse functions, inverse parabolic functions. So let's start by explaining how do we find the inverse of a function. So we've got two steps whenever we are finding the inverse of a function. So step number one is to interchange or swap the x and y values. Step number two is to just solve for y. So there's only two steps involved: to swap x and y, and then to solve for y. Now when we're dealing with a parabolic function, things change slightly because a parabolic function isn't a one-to-one function. So let's start by drawing a parabolic function. So if this is our function f, which is x squared, it's going to look like this. Let's make this slightly lower. So let's make our axis here. So this is our parabolic function, x squared. And it has a turning point, an x-intercept, and a y-intercept at the origin. Now, if we were to use the horizontal line test, by placing our ruler horizontally across the function, we would be able to see that this function fails the horizontal line test because our line intersects the function at 2 points. So this is not a one-to-one function. Now, in order to make it a one-to-one function, we need to restrict our domain. So what I mean by restricting our domain is to basically cut out or to remove a chunk of our function so that it becomes a one-to-one function. So before we do that, let's inverse our function. So we have f of x equals x squared. Now, let's rewrite this as y equals x squared. If we were to interchange x and y, this would become x equals y squared. Now, step two is to solve for y. So how do we get rid of the squared on top of y? We need to square root both sides. So if we were to square root both sides, we'd end up with the root of x. Now, we need to look at the function that we have in order to determine what part of our domain we need to remove. So if we were to substitute positive x values into this function, for example, if we were to substitute 0, 1, 2, and so on, and so on, as long as they are positive x values, we would still end up with a y value. So we are fine. But if we substituted negative x values, for example, if we substituted -1, -2, -3, -10, and so on and so on, we would end up with an error on our calculator. You can check that out right now if you want to. So because we end up with an error on our calculator, that is the area of our domain that we are going to restrict. So when we are restricting the domain, we look at the positive x side and we look at the negative x side. We substitute the positive x values into our formula and we see, will that give us a y value? If it does, we're going to leave that side. Once we substitute the negative x values and we see that it gives us an error, that means we need to remove that side. Now it can also be swapped around. For example, if the function was different, it could have been such that we would remove the positive side and leave the negative side. It depends on the function. So that is why I started off by finding my inverse function. So let's just quickly conclude. So we therefore have our inverse of f of x as equal to the root of x. Now, we are going to remove the negative side of our axis. We need to remove all of that. So that is the side that we are going to restrict. So our domain is restricted to x greater than or equal to 0. The reason that we are making it equal to 0 is because if we were to substitute x equals 0 into our inverse function, we would end up with a y value of 0. So x equals 0 does not give us an error. So we're going to restrict our domain to x greater than or equal to 0. This means all of the positive x values and 0. Now that will give us an inverse function of this parabolic function. If we were to sketch our inverse, let's start by drawing our line y equals x. So whenever we want to sketch an inverse function, we can start by drawing the line y equals x. Because we know that inverse functions are basically reflections about the line y equals x. Now, let's draw inverse function in purple. So if we were to reflect this, it's just going to be a reflection like that. So that's the inverse of our function. Now, let's move on to our next example that deals with negative x squared. So let's start off by drawing our function. So our function is negative x squared. So it's kind of similar to our previous example. The only difference is that this is a sad face function, whereas the previous one was a smiley face function. Now this is f of x. Now, our step 1, let's find our inverse function. So we remember our steps. Step 1, we need to interchange x and y. So that is going to give us x equals negative y squared. So if we want to interchange something or swap something, all we do is where we see x, we put a y. Where we see y, we put an x. Now, from here, let's move on. So we need to get rid of the negative and we need to get rid of the squared that's attached to y so that we can solve for y. So our step 1 is to divide by negative 1. The reason that we divide first instead of square rooting first is because if we were to square root negative y squared, that would give us an error. So our first step is to divide both sides by negative 1. If we divide negative y squared by negative 1, that's going to give us y squared. If we divide x by negative 1, that's going to give us negative x squared. Now, from here, we're going to square root both sides. So that is then going to give us y equals the root of negative x. If we were to put the negative sign outside the root, that is wrong because we are square rooting the entire left hand side and the entire right hand side. Therefore, we put our square root over the entire side, which is negative x. So our inverse function is therefore f inverse of x equals the square root of negative x. Now you're most likely wondering, why do we have the square root of a negative? Shouldn't that give us an error? Well, yes and no. If we were to substitute a positive value into our x position, we would end up with an error. If we were to substitute a negative x value into our function, that would give us a y value. So let's test it out. So if we were to substitute negative 1, that's going to give us 1. If we were to substitute negative 4, that would give us 2. So as you can see, if we substitute a negative value, it's going to give us a y value. We can even test it out with 0. So we have y equals the root of negative, substitute 0, and that is going to give us a y value of 0. So as we can see, all of the negative x values will give us a y value, and 0 will also give us a y value. Now, let's test out the positive x values. So if we have y equals the root of negative, substitute 1, that is going to give us an error. If we have y equals the root of negative, substitute 2, that's going to give us an error. And if we have y equals the root of negative, substitute, let's say 100, that is also going to give us an error. So that shows that all of the positive values of x will not give us a y value. It's just going to give us an error. So let's get rid of this. We now know which side of our domain or which side of our axis we need to restrict. So just to repeat once more, all of the negative values of x gave us a y value, and 0 also gave us a y value. If we substituted positive x values, it did not give us a y value, it just gave us an error. So we need to get rid of the right hand side of the graph and restrict our function to x less than or equal to 0, which will then give us our inverse. So we get rid of the right hand side of our graph and we draw our line y equals x so that we can reflect our graph. Now, let's draw a graph in purple. That looks a bit weird. Let's try once more. That looks much better. So that is the inverse of f, and we draw it using our line y equals x. Now, we've restricted our domain to x less than or equal to 0. That shows that we're using all the negative values of x and 0. So that concludes all of the theory that we are going to cover related to parabolic functions. Let's move on to some questions. So our first question is from a 2015 November exam. Let us analyze our graph and our question before we move on to actually answering our questions. So we've got question 6. The graphs of f of x equals negative x squared plus 18 and g of x equals ax squared plus bx plus c are sketched below. So we have f, which is the sad face function. Let's highlight that so it becomes easier for us to see. and we've got a g, which is the smiley face function. Let's highlight that. Okay. So we've got the graphs of f of x equals negative x squared plus 18 and g of x equals ax squared plus bx plus c are sketched below. The points P and Q are the x-intercepts of f. So we have P, which is an x-intercept, and we've got Q, which is also an x-intercept. Now, if you notice, Q is a point of intersection between our f and g graphs. So that means that Q is also the x-intercept of g. So we've got points P and Q are the x-intercepts of f, point Q and R are the x-intercepts of G. So R is also an x-intercept. S is the turning point of G, so this is S. This is our turning point. T is the y-intercept of both F and G. So this point T is our y-intercept of both graphs. Something important to take note of is that at an x-intercept, the value of y is 0. At a y-intercept, the value of x is 0. So we've now analyzed our graphs. Let's move on to our questions. So we've got question 6.1.1. Write down the coordinates of T. Now we know that T is the point of intersection of both G and F. So we can either use the function of G or we can use the function of F. But if we look closely, we don't have the function of G. Therefore, we can only use the function of F. So if we want to calculate for point T, we are going to use the function of f, and we are going to make x 0 because T is a y-intercept. So question 6.1.1. We've got f of x equals negative 2x squared plus 18, and we need to find the y-intercept, which means x is going to be equal to 0. So from here we can substitute x as 0. That's going to give us negative 2 into 0 squared plus 18, which will therefore give us a y value of 18. So we can then conclude that our coordinate T is 0 and 18. Now, let's move on to our next question, question 6.1.2, which states determine the coordinates of Q. So if we look at Q, we know that Q is an x-intercept on both G and F, but since we only have the function F, we are going to use F to find our x-intercept, which is Q. Now, if we were to use our function f to find the x-intercept, we are going to end up with the x value of P and the x value of Q. So if we look closely, we can see that P is on the negative side of our x-axis, whereas Q is on the positive side of our x-axis. So the positive x value is going to be the x value of Q, and the negative x value is going to be the x value of P. So let's try that out. So we've got 6.1.2. We've got the function f of x equals negative 2x squared plus 18, where we need to find the x-intercept, where y will be 0. So we substitute y as 0. Now we know that f of x represents y, so we're going to make that 0 equals negative 2x squared plus 18. From here, we're going to take negative 2x squared to the left. That will become positive 2x squared equals 18. From here, we need to get rid of the coefficient of x squared before we can square root. So we're going to divide both sides by 2. So 2x squared divided by 2 gives us x squared, and 18 divided by 2 gives us 9. Now from here, we can square root both sides. So we end up with x equals the square root of 9 is positive or negative 3. Now we know that whenever we square root something, it's always going to result in a positive or a negative value. So we need to figure out which value represents q and which value represents p. Now if we go back to our function, we can clearly see that q is on the positive side of our x-axis, whereas p is on the negative side. So positive 3 is going to represent q, and negative 3 will represent p. So we can conclude that therefore the coordinates of q are negative, or rather positive 3 and 0. And the coordinates of p are negative 3 and 0. Now, let's move on to our next question. Question 6.1.3. Given that x equals 4.5 at s, so at s we have an x value of 4.5. Determine the coordinates of r. So for this specific question, we're going to refer back to when we were finding our turning points of our function. There were three methods, the first being our turning point formula, the second being our midpoint formula. So for this specific question, we are going to apply our knowledge from our midpoint formula. So let's draw a quick sketch. So we have 6.1.3. So this is our point 0. This represents our origin. Let's make this our point 3, which represents Q. This is our point S, which is 4, 5. And let's make this our point R. And the value of R is unknown. That is what we need to find. So let's just call this X for now. So this is basically what we have if we were to represent this as a number line, for instance. So we know that to go from 3 to 4, 5, there's a difference of 1.5. And we know that the turning point is the midpoint of our x-intercepts. So to go from Q to R is 1.5. That means to go from S to R is also 1.5. So one way to do this question would just be to add 1.5 to the value of x. So our first method that we're going to use is just going to say the x value of R equals 4, 5 plus 1, 5. That is going to give us an x value of 6. Now, let's apply a different method. So, if we were to use the formula, so x of tp equals our x-intercepts, the sum of our x-intercepts over 2, because our turning point is the midpoint of our x-intercepts. More specifically, the x value of our turning point. Now, we know that the x value of our turning point, which is s, is 4, 5. We know that our first x-intercept, let's call it q, is 3. Our second x-intercept is unknown, and that is divided by 2. We can cross multiply 4.5 times 2, which will give us 9, equals 3 plus x. From here, we can move the 3 to the other side. So 9 minus 3 will give us an x value of r as 6. So irrespective of which method we use, we'll end up at the same answer, so that we can conclude that the x value of r is equal to 6. So let's go through both methods one more time. We know that the x value of our turning point, which is S, is the midpoint of our x-intercepts Q and R. Now, we know that to go from Q to S is 1.5, because to go from 3 to 4.5, we just add 1.5, which means to go from S to R, we just add another 1.5, that will give us 6. If we want to use our midpoint formula, all we'll do is we'll substitute 4.5 into our x value of our turning point, we'll substitute 3 into our x-intercept, and the second x-intercept, which is r, which is what we are calculating, we'll just leave it as x. Then we just solve for x from there. So we have found the x value of our x-intercept r. So let's just put this down. We know this x value is 6. Now, our next question, 6.1.4, determine the value or values of x for which the second derivative of g will be greater than 0. Now, if we look up, our function of g was not given. So we know that if we find the first derivative of a parabolic function, that will give us a linear function. And if we find the derivative of a linear function, that will give us a constant. So let's just do a quick example. Now this is question 6.1.4. So if you haven't done calculus in school as yet, you don't really need to stress if you struggle to keep up with this question, because it's still early in the year. So let's start. We know that our function g of x is equal to ax squared plus bx plus c. Now that is represented by a parabolic function. Now, if we were to derive this function, so g prime of x, that is going to give us our coefficient times our exponent, so a times 2, that will give us 2a. Now, after we multiply the coefficient times the exponent, we subtract 1 from our exponent. So 2 minus 1 will just give us 1. Now, we do the same thing with bx. So we know that the exponent of x is 1. So the exponent of x times the coefficient of x, so 1 times b, that is just going to give us b. Now, if we subtract 1 from our exponent, so 1 minus 1, because the exponent of x is 1, that's going to give us 0. So x to the power 0 is 1. So 1 times b, if we are to multiply it, is just going to give us b. So we can just exclude that. Now, c represents a constant, and we know that when we derive, constants are equal to 0. So that is our second derivative. If you notice, this is in the form y equals mx plus c, which is a linear function. So you can say that 2a represents your gradient, x, and your constant c is represented by b. So that is our linear function. So let's just put that in. So if we derive, we end up with a linear function. Now, if we were to derive our linear function, we would end up with a constant. So the second derivative of x is equal to, let's derive. So we know that the exponent of x is 1, so 1 times 2a will give us 2a. Then we subtract 1 minus 1, that is going to give us 0. So x to the power 0 is just 1. We know that 2a times 1 is then going to give us 2a. And in this case, b represents our constant. Therefore, we're going to leave that as 0 when we derive. So the second derivative of g is just the constant 2a. Now, we know that if we have an equation of a constant, if we were to draw this, it's just going to represent a constant equation, which is a horizontal line. So this is our horizontal line, and this is our second derivative. So our question was, let's go back to our question and just double check what it was. So our question was, given the value, determine the values of x for which the second derivative of x is greater than 0. So we know that g of x has a positive shape, which means a is greater than 0. So if a is greater than 0, if we were to multiply a, which is a positive number, by 2, we're going to end up with a bigger positive number. So because a is positive, irrespective of what value a is, whether it's 1, 2, 3, 4, 5, 10, 100, when we multiply it by 2, we'll get an even bigger positive number. So because it's always going to be positive, we can conclude that the x values for which g second derivative is greater than 0 will be x an element of real numbers. Or we can say x an element from negative infinity to positive infinity. So x is always going to be, or rather g second derivative is always going to be positive for any value of x, because a is always going to be positive. So if we were to draw this function of g second derivative, it's just basically going to be a horizontal straight line in the positive y area of our axis. It's never going to be in the negative area of our y-axis, because our original parabolic function was a smiley face parabolic function, or an a greater than 0 parabolic function. That results in a second derivative that is positive. So for example, let's give g of x a random function value. So let's just create our own function of g of x basically. So if we make g of x, let's say 2x squared plus 3x plus 4, and we were to derive this, this will give us g prime of x equals 4x plus 3. From here, if we were to derive it the second time, that is going to give us g second derivative of x equals 4. So as you can see, this is a positive constant. So if we were to draw our axis and create our function on the line y equals 4, that is where our horizontal line will be. Now it doesn't matter what value of a we have, as long as it's positive, it's going to be within the positive area of our y-axis when we find the second derivative. Now let's change this up and do an experiment whereby we have our negative function, which is f. So we know that f of x was given as negative 2x squared plus 18. We find the first derivative of f, that's going to give us negative 4x. If we were to derive this the second time, that is going to give us a constant of negative 4. So if we draw our axis, where we have negative 4, that is where our horizontal constant function will be. So if our original parabolic function is negative, we will have a second derivative or constant as a negative. If our original parabolic function is positive, we will have a second derivative or a constant as positive. So depending on the original function, that will affect our second derivative. So in this case, because we started off with a positive parabolic function, we will have a positive linear function as our first derivative and a positive constant as our second derivative. Thereby, because a is greater than 0, our second derivative of g will be greater than 0 for all x values. So let's move on from that question. Now, if we look at question 6.2, that is a hyperbolic function, and we are restricting our class to parabolic functions today. So that concludes question 6 from our 2015 exam paper. Let's move on to our next question. So our next question is from a 2018 exam paper. Question 5 is a hyperbolic function, so we are going to skip that. Let's move on to question 6. So let's start by analyzing question 6. So we've got in the diagram below, A and B are the x-intercepts of the graph of f, which is equal to x squared minus 2x minus 3. So that is the equation of our graph of f. Now, a straight line g, so we have f, which is a parabolic function, and we have g, which is a straight line. So let's just highlight those so they are easy to identify. So our yellow function is f, and our blue function is our linear function g. So let's continue. A straight line g through A cuts f at C. So there's a point of intersection between the two functions, which is C. So at this point, we know that f equals g. Now there's another point of intersection here by A. So we know at that point of intersection, f is also equal to g. So a straight line g through A cuts f at C, which has coordinates 4 and 5, and the y-axis at 0 and 1. So g cuts the y-axis over here at 0 and 1. That is our y-intercept of g, where x is 0. Now, M is a point on F and N is a point on G, such that MN is parallel to G. Sorry, MN is parallel to the y-axis, MN cuts X at T. So we know that MN is parallel to our y-axis. So because MN is parallel to our y-axis, it means it's a straight vertical line that is perpendicular to the x-axis, just as y is perpendicular to the x-axis. So because of that, we can make a statement M equals T equals N. So the x value of M equals the x value of T equals the x value of N, because MN is parallel to the y-axis. So if you were to draw a vertical line, all the x values on that vertical line will be the same. So the x value of M is also the same x value of N, which is also the same x value as N. So now that we are done analyzing our function, actually before that, let's just do one more thing. So we can see that the point B is the x-intercept of f, whereby y equals 0, and we can see that A is another x-intercept of f, whereby y is 0. So let's move on to our questions. So we have our first question, show that g of x equals x plus 1. So we basically need to find the equation of g of x, and that equation needs to be g of x equals x plus 1. Now, we know that in order to find the equation of a linear function or of a straight line, we need two things. We need a random coordinate and we need the gradient, or we need the value of c, which is our y-intercept, and the gradient. So in this case, we're going to use the second method because we can see that we have the c value, which is c equals 1. That is our y-intercept. So we can just make a note here. That is our value of c. So because we have our value of c, the only thing left is to find our gradient. Now in order to find gradient, we need 2 points. So we have 2 points, which is c and our coordinate of 0 and 1. So let's find our gradient. So this is a 2018 question paper. So we've got question 6.1. We need to find the equation of g. So going to find gradient first. We know that gradient equals y2 minus y1 all over x2 minus x1, and we are going to use the coordinates 0 and 1 and coordinates of c, which are, let's go back and double check, coordinates of c are 4 and 5. So going to make this my x1 value and this my y1 value. I'm going to make this my x2 value and this my y2 value. So I'm going to substitute according to that. So y2 is 5 minus y1, which is 1, over x2, which is 4, minus x1, which is 0. From here we know that 5 minus 4 is 4, and 4 minus 0 is 4. Therefore, we can conclude that the gradient of g is 1. And we know that the c value of g is also 1. So we can therefore conclude that the equation of g of x equals x plus 1. All we did was substitute into that equation, whereby our gradient was 1 and our c value was 1. Now, let's move on to the next question. So our next question is question 6.2. We need to calculate the coordinates of A and B. And now we know that the coordinates of A and B are the x-intercepts of our function f. So do we have the equation? Yes, we have the equation of the function f. So all we are going to do is find the x-intercepts of f. And we know x-intercepts are where y is equal to 0. So question 6.2, we've got f of x equals x squared minus 2x minus 3. And we need to substitute y equals 0 in order to find the x-intercept. So we'll substitute y as 0. It's going to be x squared minus 2x minus 3. Now, if we were to factorize this, we need to find the factors of negative 3 when added give us negative 2. So we know the factors of negative 3 are positive and negative 3 or positive and negative 1. So let's add them up. Let's start with positive 3 plus positive 1. That gives us 4, which is wrong. Let's look at negative 3 and negative 1. That's going to give us negative 4, which is wrong. We need negative 2. Now let's change them up. Let's use negative 3 and positive 1. That gives us negative 2. So that is correct. So those are the factors that we are going to use. We are going to use negative 3 and positive 1. So we've got x minus 3, x plus 1 equals 0. From here, we can conclude that x is equal to 3 or x equals -1. Now, we needed to find the coordinates of A and B. We have two values, a positive value and a negative value. So we need to see which value applies to A and which value applies to B. So as we can see, A is on the negative side of our x-axis. Therefore, we are going to give A the negative value, which is -1. And B is on the positive side of our x-axis. So we are going to give it the positive value, which is 3. So let's write out our coordinates. Therefore, our coordinates of A are -1 and 0, and our coordinates of B are +3 and 0. So those are our x-intercepts of our function f. Now, let's move on to question 6.3. We need to determine the range of f. So our range is dependent on our shape. Because f has a positive shape, we are going to start from our minimum value and go up for range. So start with a sketch. So this is our function of f, and this function has a minimum value at our turning point, which is our q value. Now, our range represents from our minimum value all the way going up. So we will start by finding the q value. Now, in order for us to find our q value, we have one of two options. First, we can find our x value of our turning point and then find our y value of our turning point, which is our q value. Alternatively, we can complete squares on our function f, which will give us our q value. So I'm going to use the method whereby I use my TP formula, which is finding the x value of my turning point, and then I'm going to find the y value of my turning point. So let's quickly check what is our function. Okay, so our function of f is 2, or rather x squared minus 2x minus 3. Now my formula of my x value of my turning point is xtp equals negative b all over 2a. So I'm going to carry over the negative. Then I need to substitute my value of b. Now I know my value of b is the coefficient of x, which is -2. Now be very careful, don't just bring down -2 because you see that there's a negative in front of this formula. Always remember to first bring down the negative, then substitute -2. If you were to just bring down -2 only, that would affect your final answer. The sign of your final answer would be wrong. So always step number 1, bring down your negative, then substitute your negative or your b value. Now we bring down the 2. Now we need to substitute a. We know that a is the coefficient of x squared, which is 1. From here we know that negative times -2 gives us +2. 2 times 1 gives us 2. Now we can conclude that our x value of our turning point is therefore +1. If we want to find the y value of our turning point, we substitute +1 into our original function. So that's going to be 1 squared minus 2 times 1 minus 3. So 1 squared is 1 minus 2 times 1, which is 2 minus 3. And that is going to give us 1 minus 5, which is -4. Therefore, our y value, or we can say our q value, is equal to -4. So this is equal to -4. So the range of our function f starts at -4, touches all the y values from -4 all the way up to infinity. So let's write down our range. It's going to be y greater than or equal to, so we use greater than or equal to because it's a positive shape function. If it was a negative shape parabolic function, we would use less than or equal to. So this is going to be y greater than or equal to our q value, which is -4. An alternative representation would be y an element from our minimum value, which is -4, all the way to our maximum value, which is positive infinity. Now I've used squared brackets because we are including the value of -4 because our graph touches -4. If our graph didn't touch -4, if it was from above -4, we would use rounded brackets and we wouldn't use the equal to sign. Now let's move on to our next question. So our next question is question 6.4 that states mn equals 6. So that means that the distance from m all the way to n is 6 units. So question 6.4.1, determine the length of OT if t lies on the negative x-axis. Show all your working out. So we need to find the distance OT. So if we find the x value of t, that will give us the distance OT. So OT is from our origin all the way to our point T. We need to find this length. So if we find the x-coordinate of t, let's say for example the x-coordinate of t is -5, we know that our distance OT will therefore be 5, because remember distance cannot be negative. So we just take the value, we ignore the sign. So our approach is going to be finding the value of t. So let's start with that. We know that in order for us to find the value of t, we need to create an equation from mn and find that x value. So in order for us to create an equation from mn, what we can do is we can find the difference. So let's start by creating our equation. So we'll state 6.4, we know that mn equals 6. So 6.4.1, we need to find the coordinate, or rather the distance OT. Now, if we want to create an equation, because we already know that mn equals 6, so let's find the equation mn, or rather a different way of putting it is let's find the distance mn. So we know that mn is going to be the top function minus the bottom function. That is how we are going to find that distance mn. It's kind of like finding displacement. For people that are dealing with physics or people that take physics as a subject, you will be more familiar with this. So the displacement mn is 6 units. So in order for us to find displacement, we're basically just subtracting the two functions, which will give us the distance in the middle, which is 6. So we now need to create an equation to find that displacement. So all we need to do is subtract the function at the top minus the function at the bottom, and that is going to give us our distance mn. So we know that our function on top is our function f, whereas our function at the bottom is our function n. So let's do that. So our function on top touches m, and our function at the bottom touches n. So we're basically stating m minus n. So let's find our function. mn is then going to be equal to the function of f of x minus g of x. So mn is then going to be x squared minus 2x minus 3 minus, now we need to substitute our function of g of x. The reason I'm using brackets is because there's more than one term in g of x, and if we have a negative sign preceding what we are going to substitute, we always put it in brackets because this negative sign is going to affect whatever comes in this bracket. So we know that our function g of x is x plus 1. So let's simplify that. Mn is therefore equal to x squared minus 2x minus 3. And now this negative sign times x is then going to give us a value of negative x. And this negative sign times positive 1 is therefore going to give us a value of negative 1. So let's simplify that because we have like terms. So x squared, now negative 2x minus x gives us negative 3x, and negative 3 minus 1 gives us negative 4. So this is basically our equation of our displacement between m and n, or the equation of our distance between m and n. Now we know that mn is 6 units. So we can substitute that 6 units and then solve or simplify. So we have minus 3x minus 4 minus 6 equals 0. So from this point we are going to simplify and solve for x. So our equation is now x squared minus 3x minus 10 equals 0. So if we were to factorize this, we need factors of negative 10. When added up gives us negative 3. So we know the factors of negative 10 are positive and negative 1 and positive and negative 10. The other factors are positive and negative 2 and positive and negative 5. So let's test them out. If we were to add positive 1 plus positive 10, that will give us positive 11, which is not what we want. We want negative 3. If we were to add negative 1 plus negative 10, that will give us negative 11, which is still wrong. If we were to add negative 1 and positive 10, or positive 1 and negative 10, it still will not give us negative 3. So we can get rid of those factors, they don't work. Now, if we look at positive 2 and positive 5, that's going to give us positive 7, which is not what we want. If we look at negative 2 and negative 5, that is going to give us negative 7, which is not what we want. We want the factors of negative 10, when added, should give us negative 3. So if we take positive 2 and negative 5, so let's try it out, positive 2 and negative 5, that's going to give us negative 3, which is what we want. So that is going to be x plus 2 and x minus 5 equals to 0. Therefore, we have x equals negative 2 or x equals positive 5. Now, we need to determine whether the coordinate of t is negative 2 or positive 5. Now, if we go back to our diagram or our function, we remember, or we know that t is on the negative side of our x-axis. So that means that t will have a value, or an x value of negative 2. So that means that m has an x value of negative 2, t has an x value of negative 2, and m, or rather n, has an x value of negative 2. Because we previously stated that the x value of m, t, and n are the same. Now, because we've identified that the x value of t is negative 2, we know that the distance OT is going to be positive 2. Because we basically ask ourselves, how many steps do we need to go from 0 to -2. So it's 2 steps. We go from 0 to -1, from -1 to -2. And keep in mind, distance can never be negative because it's a scalar unit. Therefore, we just take it without the sign. So we can therefore conclude that the distance OT is going to be 2 units. Okay, now that is our question 6.4.1. Now let's move on to question 6.4.2. Our question 6.4.2, hence write down the coordinates of n. So we know that if we want to find the coordinates of n, we already have the x coordinate of n, which is -2. So all we now need to do is find the y coordinate of n. So we previously found the t coordinate or the x coordinate of t as -2. And because mn is parallel to the y-axis, it means that all the x values on the line mn are equal or are the same. So because the x-coordinate of t was -2, that means the m and n x values are also -2. So that is how we arrived at the x value of n as -2. Now, because the point n is on the equation or on the line G, we therefore use the equation of G to find the y value of n. So, just to repeat once more, I am going to substitute my x value of n into my equation of G because n is a point on G. So, our function G or our equation of G is y equals x plus 1. So let us substitute x as -2. So question 6.4.2, we are going to find g of -2. So that is going to be -2 plus 1, which therefore gives us -1. So we can conclude that the n coordinates are -2 and -1. So those are our n coordinates. Because n was a point on the line G, we used the equation of G, substituted the x value of n in order to get the y value. Now, let's move on to our last and final question, question 6.0. It's not actually our last question, it's our second last question. So question 6.5 is determine the equation of the tangent to f drawn parallel to G. So let's look at our function G. So our tangent is to the function f and it must be parallel to G. So let's just draw a random line that is parallel to G so that we have a basic kind of a reference or something to use as a visual representation. So this is going to be our tangent to f. It's just a way for us to visually represent our tangent, for us to just see something that we can use. So this is the x value of the point of contact, and this is our tangent. So if we need to find the tangent to f, a tangent is just basically a straight line that touches the graph at one point. So just as normal straight lines, if we want to find the equation of a straight line, we need two things. We need either the c value and our gradient, or we need a random coordinate and our our gradient. So because we don't have the c value of our tangent, I'm going to use the second method, which is to have our gradient and a random coordinate, and use those two things to find the equation of our line or our tangent. So because it's stated that the tangent is parallel to G, that means the gradient of G is the same as the gradient of our tangent. So let's go down here quickly. So question 6.5, the gradient of G is equal to the gradient of our tangent, which is then equal to 1 because G is parallel to our tangent. Something important to remember is that whenever two lines are parallel to one another, their gradients are always equal. So because the function g was parallel to the tangent, their gradients were equal. So we have our first requirement for calculating the equation of a line. We have our gradient. Now the next thing we need to find or to determine is our coordinates. So we need a coordinate on the line of our tangent. So let's go back to our graph and see how can we find the equation of our tangent. So we have our gradient, we need a coordinate. So we can find the coordinate of the point of intersection between our function f and our tangent. Now, a way we can do this is we can use the method of finding gradient from calculus and then substitute our gradient and solve for x. So let's use that method. So if we want to find the gradient of the tangent, we know that we are going to use the function f because the tangent is in contact with the function f. And the point of contact between our tangent and our function f, the gradient is equal at that point, which means that the gradient of f at that point is equal to the gradient of our tangent. So if we were to derive f, so let's first start by writing out our f formula, which is x squared minus 2x minus 3. So if we want to find gradient using calculus, so let's just make a note of that. So we are finding gradient using calculus. So our step 1 would be to derive. So to find f prime. Our step 2 would be to substitute the x value of our point of contact. And our third step would be to simplify. That is how we would find the gradient of our tangent and of f at that point if we were using calculus. So we're going to use a similar approach, but instead of substituting x and finding our gradient, we're going to change it up a bit and substitute our gradient to find x. It's kind of like a converse essentially, or a reverse method. So we know that our first step is to derive. So f prime of x is then equal to now our exponent times our coefficient, which is 1 times 2. That is going to give us 2. Now we subtract 1 from our exponent, so 2 minus 1 is just 1. Now we move on to the next part. So the exponent of x is 1, so 1 times negative 2 is negative 2. 1 minus 1, so we're going to subtract 1 from our exponent. So 1 minus 1 gives us 0. X to the power 0 is just 1. 1 times negative 2 is still negative 2. So our first derivative of f is 2x minus 2. Now, you can think of this as the equation of our gradient essentially. So this first derivative is basically the equation of our gradient. Once we substitute the x value of our point of contact between our tangent and our function, that will give us the actual value of our gradient. But now in this case, we don't have that x value, but we have our gradient. So let's substitute our gradient, which is 1 equals 2x minus 2. So from this point, we are now going to solve for x. So let's just make a quick side note that f prime of x is equal to 1. That is our gradient. So if we were to solve for x, we would then end up with 3 over 2. So this is our point of contact between our tangent and our function of f. So this x value that we have found is the point of contact between our function f and our tangent. So basically we've got this function f that looks like this, and we've got this tangent to our function f that we need to find the equation of. So this value x that we found is our point of contact, 3 over 2. So let's move this diagram to the side so that we can continue solving our question. So now that we have our x value of our point of contact between our function and our tangent, let's now find the y value. So we're going to use the original function of f and substitute 3 over 2 in order to find our y value. So we have 3 over 2 squared minus 2 into 3 over 2 minus 3. Now, once we put this onto our calculator, we then have a y value of negative 15 over 4. So that is the coordinates of our point of contact between our tangent and our function f. Now that we have both our requirements, our gradient and our coordinate, we can now find the equation of our tangent. So we know that our equation of a straight line is y equals mx plus c. From here we can substitute our gradient and our coordinates. So our gradient is m equals 1. Our coordinates are 3 over 2 and negative 15 over 4. So let's substitute that in. So y is negative 15 over 4 equals our gradient, which is 1, times our x value, which is 3 over 2 plus c. So we need to find our value of c. In order to do that, we are going to take 3 over 2 to the left, because we know 1 times 3 over 2 will remain 3 over 2. So c will be equal to negative 15 over 4 minus 3 over 2. Now, once we put negative 15 over 4 minus 3 over 2 into our calculator, we should end up with a value of c as negative 21 over 4. Now this value of c is where our tangent cuts the y-axis, which is our y-intercept. Now that we have our value of c and our value of m, all we need to do is substitute both values into our equation of our straight line. So we have m equals 1 and c equals negative 21 over 4. So let's substitute that in. So we have y equals 1, which is our gradient, times x minus our c value, which is 21 over 4. So we can therefore conclude that the equation of our tangent is x minus 21 over 4. So just a quick recap of what we did. Our goal was to calculate the equation of our tangent. Now, because it was given that our tangent is parallel to the function of g, we knew that the gradient of our tangent is equal to the gradient of our function g. So that allowed us to find the gradient of our tangent as 1. After we found the gradient of our tangent, we then needed a point or a coordinate on our tangent. So we were able to use calculus to find the point of contact between our tangent and our function f by using the find the gradient method. So when we're finding the gradient in calculus, we substitute the value of x, and then we get our gradient. So what we did was we derived and then we substituted the value of our gradient in order to get x. So it's kind of like we did it in the reverse essentially. So we substituted gradient, which allowed us to find x. Once we found x, we substituted x into our original function in order to get y. So we then had our gradient and our x and y value, our random coordinate. Once we had that, we just substituted those three values into our equation of a line, which allowed us to find our c value. Once we found c, we were then able to substitute our gradient and our c value into our equation of a line in order to get the equation of our tangent, which is y of our tangent equals x minus 21 over 4. Now that was our question 6.5. Let us now go and find, or rather solve, for question 6.6. So question 6.6 states, for which values of k will f of x equals x squared minus 2x minus 3 and h of x equals x plus k not intersect? So something important to take note of is that the gradient of this line h is 1, which means that this line of h is parallel to our tangent. Now, this question wants to know for which values of k. Now, keep in mind, k is going to represent our c value. K is going to be the y-intercept, because if you look at the format of this line h, it's y equals mx plus c. So c is going to represent k. So we basically need to find for which values of k will our line h not intersect f. So if we go back to our tangent drawing, we basically have this line h. So before we draw our line h, let's label these things. It's tangent. So we now have our line h that is not allowed to intersect the function f. And the gradient of h is the same gradient of our tangent. So if we look at our tangent, we can see that our tangent cuts or comes into contact with f once. So basically, if we want to find a line that is not going to touch f, this line has to be below our tangent. If it's above our tangent, it's going to intersect f. So an example, if our line is above our tangent, it's going to cut f, as you can see. All those lines above h, or rather above our tangent, are cutting or intersecting f, as you can see. So if we want a line that is not allowed to intersect f, that line has to be below our tangent. So as you can see, if you make a line below your tangent, it's not going to cut f or intersect f. So basically, our value of k needs to be below the value of negative 21 over 4, because essentially k is like c. So this c value is negative 21 over 4, and we are not allowed to go higher than negative 21 over 4, because if we do, it's going to start intersecting f. So the answer to this is k less than negative 21 over 4. So if k is less than negative 21 over 4, the line of h will not intersect f, because it's going to be lower than f, and if it's lower than f, it cannot come into contact with f. Because if we were to draw, let's just draw a y-axis so that we can explain a bit further. So let's make this our y-axis. And let's make this point negative 21 over 4. So if we have our line h, this line h has to be lower than 21 over 4. Because if it's above 21 over 4, negative 21 over 4, it's going to start intersecting f. So our k value has to be less than 21 over 4. As you can see, if it's less than negative 21 over 4, it's not going to intersect. And that is the final question of our 2018 November exam paper.